Okay, hello everyone. Welcome back to your YouTube channel and welcome to this very important and beautiful video. Okay, as you must be aware, some of my master students they are taking a project related with HVDC link, and some of them they are interested on simulating the steady state performance of HVDC interconnector that is embedded inside a classical AC system. And the simulation tool that we are using is DIGSILENT PowerFactory. As a consequence, today I have a very short video with a short explanation about this situation related to HVDC links. Okay, as you must be aware, there are different type of HVDC links. There are different applications. For instance, if you need to interconnect to different areas with different frequencies, you can use a classical HVDC system point-to-point connection, but also there are new applications like the integration of offshore wind power using undersea cables. Okay, the point-to-point interconnection has been quite useful, especially when we are using different frequencies. That is the case, for instance, the example from Brazil, Itaipu, that is connecting Brazil and Paraguay. Okay, and has been very well developed. However, most recently, we are using HVDC Link for offshore wind power because they offer several advantages, especially for the use of DC cables, undersea cables, for the interconnection with far wind farms. However, the topic today is the most important thing is the DC link embed inside a classical AC system. Okay, this situation started in 1970s in the United States in Los Angeles when the first HVDC link was embedded into a AC classical AC system. There are few functionalities that you can take the advantage of having a very controllable device like the HVDC system. However, 1970s was a very bad time for HVDC system because we have the very old technology based on thyristor. Here in this slide, as you can see, there are different type of using HVDC system inside AC system. What you need to understand is that they can use, for instance, a coupling point between the AC side and the DC side, and the point-to-point connection is basically a point where you can a path where you can move some AC power, okay, or DC power. And the idea is there are many advantages of this, like for instance congestion management, or for instance voltage control. There are several features and several advantages of having this. But today I'll be working with one of these HVDC links that is in parallel with a AC link. The idea of having a DC transmission line in parallel with that HVDC link is basically to have a better control of the active power that is moving on the AC side. AC has been for many years in the electrical power system. However, they have some limitations regarding what the control of active and reactive power is. And the DC link is coming to help in this kind of matter, okay? There are many applications around the world where HVDC link has been embedded inside the classical AC system, and many features has been improved. For instance, for removing inter-area oscillation, a special controller, damper controller, can be installed using the HVDC link, and this has been used in many countries around the world in order to improve the system stability, the voltage control, but many other situations related with cascading failure. And that is the reason that, for instance, in the UK, we have the Western HVDC link connecting Scotland and Gales. Um, if you look on the right-hand side, we have here a equivalent of the GB system, and you can see two terminals, AC terminals, that they are connecting the north part, Scotland at Hutterstone, and going down to Gales in the deep side, okay? The HVDC link is a power of 2.2 gigawatts and around 240 miles undersea cables, okay? The idea is that we want to take the advantages of having the AC system in parallel with this HVDC link. The idea is to increase the power transmission capacity between the north and the south, and that is one of the objectives, increasing the Anglo-Scottish capacity by more than 6 gigawatts. But also, the undersea cable look like a better solution when we have to reduce the visual impact and also another kind of environmental issues. This HVDC link is basically a line commutate converter. We are talking about the LCC technology that is moving the power using undersea cable, using a very specific DC cable between the Hotterstone substation and the D-side substation. And the idea is that this HVDC link has been equipped with several controllers, and the idea is to increase the performance, especially in reduction of inter-area oscillation between the north and south of the GB system. Of course, one of the objective is also controlling the DC power and as consequence modulating the AC power inside the system. What I will do now is I will use one of the systems that I have been using before. This is the classical example I showed you before. This is the classical generic 12 bus test system for wind power integration. What I will do is here in the bus bar 7 and 8, my plan is to install a HVDC link in parallel with this AC line. The idea is to show you how to use the model inside the DIGSILENT PowerFactory, but also how to control the DC power on the DC link in order to control the AC power on the other line. And it's very important that you understand that the DC link can help and support the AC side, because the DC link has several controllers that they can be defined and they can be set in order to enhance the features and the capabilities of the AC system. That is one very important point that you must take aware, that the DC links, they came to help and support the classical AC system. But right now, what we will do is going to Power Factory and start the installation of this HVDC link between bus bar 7 and, and 8. Okay? Right now we are here in the DIGSILENT PowerFactory. As you can see, this is the test system that we have been using before. This is the generic 12 bus test system for wind power integration studies. And this system we have used it before, especially for load flow, for power flow, in order to show you the phase shift in delta star transformer. What I will do right now is running a load flow. As you can see, there are some results, and I will focus specifically in between bus bar number 7 and the bus bar number 8. Okay, we will focus in that area. You can see there is a power flow going from bus bar number 7 to 102.5 megawatts. They are departing from bus bar number 7, and then 106 megawatts are arriving to bus bar 8. Of course, this is a AC transmission line. They are resistant, they are reactants, and as a consequence, there are some losses over there. Specifically, you can see they are 18.8 ohms, and that is the series resistance for that system. You can run the calculations, and you can see the power that is dissipated is the difference between 202 and 196 megawatts. Okay. What we will do now is I will install over there the HVDC link, and right now I am just changing the size of the bus bar to include one more component. And DIGSILENT PowerFactory has a very interesting and very useful component. There is an object over here. You can see this is the HVDC link, specifically LCC technology, and you can take from there just a click, and then you can connect the DC link between the two bus bars, in this case 7 and 8. And that is what I will do right now. Okay. Right now, click here in bus bar number 7. Now click in bus bar number 8. And right now, voila, we have a HVDC link, okay? We have, you can see over there, the symbol for two converter station using the classical thyristor, because this is a LCC link, okay? This is the first technology, the oldest technology for HVDC systems, commercial. And right now you have installed over here this converter, this DC link, okay? What I will do now is basically I will include a name over there, HVDC-LCC 7 and 8 for the connection. And right now I will go for the data that we need to run the load flow, okay? In this page, as you can see, there are information for the conditions that you need to define for running the load flow. But before that, we need to define an object, a type, for this HVDC link. Okay, this object, this is the element, but the element require a type. And what I will do now is a new project type. I will define a name. In this case, I will say HVDC link LCC type FGL, and I will keep 1000 megawatts as the rate power. And now we have two converter stations, one sending and receiving. And what I will do now is I will define the AC rate voltage. Remember, this system is connected to 345 kV, 345 kV on the AC side, okay? And what I am doing right now is defining the rate voltage for this converter, and we will keep 1000 megawatts as the rate power of the converter station, okay? We are using 1000 megawatts converter station, converter 1, converter 2, and both sides, they are defined by 345 kV. Also, if you want to create a more detailed and more realistic model, you can include losses, non-load losses, and switching losses, and so on. However, I will not cover this in this video. That is a subject for my course on power electronics modeling using the DIGSILENT PowerFactory, okay? What I will do now is we will keep 1000 megawatts, 345, and I almost make a mistake, 345 kV. Okay, right now we have two converter station, 1000 megawatts, and we assign the type for this LCC converter station into the element, okay? Right now we include the type into this element, and now is the very important moment, because right now we need to define the load flow conditions. And HVDC links, they are very different. They are more complex than the classical AC system. We need to define condition for the rectifier station and for the inverter station. For the rectifier controller, we need to define the control mode. And as you can see over there, there is a control mode that is right now saying PDC. PDC means that the rectifier is only controlling the active power or DC power that is injected into the DC link. In this case, I will say this is the power, and the power is controlled to be 100 megawatts, okay? That means that in this case, the HVDC link will be sending 100 megawatts from bus bar 7 to bus bar number 8. And that is the function of this rectifier. For the inverter, the situation is a bit more complex, because the inverter has AC and DC side, and they are a controller. And as you can see over here, we have UDC and gamma controller. UDC means that the converter is just taking care of the DC voltage side, and gamma, I not explain that here, but if you take my classes on power electronics, you will learn more, okay? It's very important and very sensible, the definition of this set point for the voltage, okay? And that is the reason that I need to run some explanation here about this set point, because you cannot use over there a generic value or a value without proper definition or proper calculation, okay? What is important that you understand is that the voltage set point must be properly defined, or otherwise the load flow will never converge. or what I'm trying to say, if you put a ground setting over there, you will get an error when you are trying to run the load flow, okay? For that reason, we need to set up this voltage in a very precise and very well-defined way. But the good news is DIGSILENT PowerFactory has a very, very good technical reference. And inside that technical reference, you can get all the information about the modeling, about the equations, and all the details related to this HVDC link. Right now, I am opening the help, and I am going to the technical reference, looking for the technical reference of the power electronic converters. And here we are in power electronic devices, and as you can see, there is a HVDC link for LCC, and that is the one that I am looking for. I will open the technical reference, and right now we are inside PowerFactory 2020 technical reference for the HVDC-LCC. And what I will do is I will move through this technical reference, technical documentation. As you can see, you can include several different models, including 6 pules, 12 pules, and 24 pules, different kind of bridges used in thyristor, okay? However, I will stop here at the section that is called load flow analysis, and I will go to calculation converter parameters, because that is the section that I am looking for. As you can see, there is an equation below, and that is an equation that establishes the connection between the DC side and AC side voltages. Okay, equation number 5 in your screen is telling you what should be the value for the DC side based on the value that you have for the voltage on the AC side. As you can see, it's 3 times square root 2 divided by pi. And that is extremely important that you know that value. Because below that value, the rectifier must be able to cope with the voltage and supply the power in a proper way. But if we go above that voltage, the inverter will not be able to deliver the power to the AC side. For that reason, this equation is extremely important and making the connection between the AC voltage and the DC voltage, okay? For the system that we are working, remember that the AC side is using 345 kV, 345 kV. For that reason, if we apply this formula, this equation, 3 times the square root 2 divided by pi, we will obtain a number that is 465.91 kV. For that reason, with 400 kV, this should be doing the job. We keep 400 kV, and right now what I will do is to show you the results, okay? I will rotate those result boxes in order to make easier to see the results, and I am rotating the result boxes. And as you can see on the bus bar 7, they are 100 megawatts departing from bus bar number 7, and they are arriving 99.4 megawatts to bus bar number 8. Of course, there are some active power losses related with the transmission on the DC side, but we are now changing the active power to 0. And as you can see, I can control the DC link to 0, and the situation come back to the original 202 megawatts going across the AC line, okay? What I am showing you is that the DC system can be controlled from 0 power, and right now we are changing to 200 megawatts the DC link, and right now we got 200 megawatts on the DC link, but we are still having 57.6 megawatts at the AC line, okay? Now, a new try. Now let's let's go for 200 megawatts. 250. As you can see, the voltage on the AC side is starting to go down, but we reduce a bit more the power on the AC line. However, something that you need to take care about is the reactive power moving through the line, okay? It's very important that, okay, you can minimize the active power, but what's happening if we change right now the situation and we go back to 100 megawatts? Right now we are using 100 megawatts. And what I want to show you is what's happened if we change the voltage, the DC voltage, to a value that is above 465.91 kV, okay? Okay, right now, if we put over there a value, let's see, let's put a value above 465. Let's use, for instance, 500. Bam. Right now you got an error because the load flow is not possible to be solved. And what you need to understand is that we cannot put any value on the voltage set point. Those values must be properly defined in order to avoid the no convergence of the load flow. If you put a set point that physically is impossible to be delivered by the power converter, of course, PowerFactory will tell you, okay? Right now we are changing again, and as you can see over here, we are still having a load flow if we apply a voltage that is below 465 kV, okay? Of course, on the other side, on the transmission line, you will keep having some load flow, but we demonstrate in this video that using a DC link, we can change the active power and keep working, okay? And of course, this model have also RMS and AMT possibilities for modeling and simulation. However, I'm not covering this in this video. If you want to learn more about dynamics of HVDC links, please attend to one of my trainings about modeling and simulation of power electronics using DIGSILENT PowerFactory, okay? Well, finally, I introduced the concept of the element HVDC-LCC, and I use here to show you how we can control the power, the megawatts moving through the HVDC link, and as consequence, there are some benefits on the power flow reduction on the AC grid. Well, this is all for this video. Thank you very much for watching.